Hey everyone, here's my Lab 3 circuits video. Um, so the introduction. So the purpose of the lab is to apply the principles of energy conservation, the loop rule, and the current conservation, conservation in steady-state conditions to analyze circuits and resistors arranged in series and parallel circuits. Understand the current voltage in these circuits with resistance and capacitors. Find the time constant using experimental track values via a multimeter, and measure the electric current and potential difference. So the principles that we have is that the natural log delta V over delta equals negative T over RC. That's to find the time. The RC constant. Resistors in the series is the R1 plus R2, and the resistance in parallel is 1 over R1 plus 1 over R2 is the total resistance of a parallel circuit. The Ohm's law, we got V equals IR, which is important to find the resistance in the current value. Other things is the node rule and the loop rule. So in our next one, we're going to talk about the Ohm's law, V equals IR. Kirchhoff's loop rule is the V of everything in the circuit is going to equal 0, and then the I in equals I out. Whatever comes into the node is going to go out and equal the same value. The capacitance equals C equals Q over V. So preview of our main results is that the R47 is calculated to be 48 ohms. The resistance 100 is 100 ohms. Ammeter was 0 ohms. Time of charging capacitor equals the time of discharging. So experimental time constant we got was 5.9 seconds. Computed time constant was 6 seconds. Experimental value of the current was 0.02 amps, and the actual observed current was 0.02 amps. And this was our circuit, the model. We have 2 batteries and 2 ammeters, and 147 ohm resistor and 100 ohm resistor. So here is the experiment. That's a picture of the experiment that we did. So the assumptions we had was it is in a steady state, negligible resistance amongst other components. The system is the circuit, the surroundings is everything around it. The initial conditions are the 100 ohm resistor, 47 ohm resistor, and things I talked about before. So the current value that we predicted was going to be 0.02 amps from the V equals IR formula, and the delta V equals 47 ohms across the first resistor is 0.97. Delta V is 2 volts across the second resistor. That's our predicted values. So days and calculations, we use this graph to sort of do that. So A to B has 3 volts, B to C has 0 volt change, C to D has a negative 0.96 volt change, D to E equals 0 volts, E and F equals negative 2.0 volts, and then the rest are 0 volts. So resistance, we calculate using the graph. We got negative 0.96 over 0.02, we had 48 ohms. The 100 resistance was negative 2.04 divided by 0.02. We got 102 ohms, and the RY resistance was 0, and the ammeter resistance was 0 as well. The potential sources of error for this experiment and the experiment I'm about to describe later on is that there could be inaccurate measurements of and calibrations of the ammeter and the voltmeter, incorrect measurements of the voltage and times, instrumental errors in multimeters, and human error due to recording the times in the next part. So the second part has us making an RC circuit. The systems and surroundings of the RC circuit was that the system is the RC circuit and the surroundings is everything outside. The conditions were the 9-volt battery that we used, the 10 ohm light bulb, the 0.2 F capacitor, and we repeated the experiment twice with a 20 ohm light bulb. So the predicted conditions for the RC circuit was 30 times 0.2 equals 6 seconds, and the experimental value that we got using the values that we calculated, we put in a graph, and we figured out the slope was negative 1 over negative 0.196, 5.9 seconds, so that's pretty close to our predicted value. The procedure was we would run the circuit over and over again, measuring the time it takes to charge and discharge the capacitor by looking at the light bulb and using a stopwatch to find the charge and discharge times. So the data and calculations, so for the R10, and that should say R20, sorry about that, the bulb charging and discharging was 12 seconds and 14 seconds, and 28 seconds and 29.5 seconds, so off the bat. We got pretty equal charging and discharging of the light bulb, so that's pretty good. So this means that double the time for the resistance is the double the time of the charging. So for the what if question, they ask us, you charge the capacitor with no resistor in the circuit, how quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain, use an ammeter to measure how long it would take to charge the capacitor when it connects directly to the battery in the ammeter. Discuss why the measured time is different from the predicted time. In an ideal model, a capacitor without a resistor would charge instantaneously, since the equation Vc equals V0 1 to the negative E approaches the full charge immediately when R equals 0R or 0. However, in real life, this is impossible because the wires, the battery, and the capacitor still have inherent resistance, stopping infinite current. The ammeter's resistance will slow down this process, so therefore it will be impossible for the capacitor to charge like the model predicts, and it would always be slower than the question asks. So some of the stuff that were important in this experiment was that the node rule and the loop rule were very important, the Kirchhoff's rule, and then the another thing to talk about was the the difference in capacity, the difference in resistance was very different because of all the things that I just talked about in this question.